Welcome to This Explainer. Today, we are unlocking one of the absolute coolest secrets in modern tech. We're going to look at the mathematical underpinnings of how AI actually learns language. I mean, think about it. How does a system built entirely on vectors and weights develop such an incredibly nuanced grasp of human semantics? Well, let's dive right in and find out.
So consider this core linguistic mystery. How does a computer actually know that cherry goes with pie? Because to a machine, cherry is literally just a string of data, and pie is just another string of data. To understand how AI links them, I want you to imagine a massive party. You're at this party, you look over and you see two people standing next to each other. Now, are they hanging out because they came together and are, strongly associated? Or is it just a really crowded room and they just happen to bump into each other by pure chance? That is exactly the question a computer has to answer when it sees two words sitting next to each other in a sentence.
Okay, here's our roadmap for this explainer. We're going to start with how computers traditionally link words, introduce the magic of PMI, crunch some Wikipedia numbers, tackle the problem with negative values, and finally look at fixing rare word bias.
Let's start with part 1, how computers link words, and specifically the co-occurrence problem.
The absolute most intuitive way to link words, right, is just to count how often they appear together. If you look at these raw co-occurrence counts from Wikipedia, target words like cherry and digital are mapped against context words. We can see cherry and pie appear together 442 times. That seems like a pretty strong link. But wait, what about a word like data? Highly common words appear next to almost everything. If we just rely on these raw counts, we really don't know if words are truly associated or if one of the words is just so overwhelmingly common that it's bumping into everything else at our metaphorical party. We definitely need a smarter mathematical approach here.
And that brings us to section 2, the magic of PMI, or pointwise mutual information.
Originally formulated way back in 1961 by Robert Fano, and then adapted for language by Church and Hanks in the late 80s and 90s, pointwise mutual information is a measure of how much more two words co-occur in a corpus than we would expect by pure random chance. It draws on a pretty brilliant intuition. We shouldn't just ask how often two words are together. We should ask how often they're together compared to what we'd expect if they were completely 100% independent of each other.
Let's visually deconstruct this formula, because it's all about how the equation is balanced. Step 1, the top part, the numerator. This represents our observation. It's the probability of seeing the two words together. Step 2, the denominator, represents our independent expectation, the probability of word A multiplied by the probability of word B. This basically tells us what happens if they just randomly bump into each other. Finally, step 3, we take the base 2 logarithm of that ratio. This gives us our true estimate of association. If that ratio is way bigger than 1, they are absolutely hanging out on purpose.
Moving right along to section 3, crunching the Wikipedia numbers. Let's pit cherry pie against digital data.
Now, what's really interesting here is that to get our data ready for the PMI formula, we first have to convert those raw counts into joint probabilities. We're calculating the likelihood of seeing a specific word and context together out of the entire corpus, like, for example, the marginal and joint probabilities of information and data. Basically, we're mathematically prepping the data so we can plug it directly into our PMI equation.
And this brilliantly illustrates what happens after we run the math. Just look at the striking contrast. Cherry and pie have a massive PMI score of 4.38, meaning they are intensely associated. Strawberry and sugar score a 5.51. But cherry and computer, they get a big fat 0. Even if they happen to appear in the same article a couple of times, the math proves it was just random chance. The noise completely vanishes and the true semantic meaning emerges.
But of course, there's a plot twist. Section 4, the problem with negatives and when PMI essentially breaks.
The big snag here is that PMI values can actually range from negative to positive infinity. A negative PMI implies two words are co-occurring less often than expected, like they are actively avoiding each other. But negative values are notoriously unreliable. If two words are already incredibly rare, trying to mathematically prove they appear together even less than random chance, you would need impossibly enormous text corpora to verify that. Honestly, human beings can't even realistically judge if two rare words are just unrelated or actively repelling each other.
So the solution researchers came up with was brutal but super effective. We contrast the original PMI with something called positive PMI or PPMI. Since those negative numbers require impossible amounts of text to actually verify, PPMI just cleanly replaces all negative values with exactly 0.
If words occur together less than chance, we just call it 0. And if they have literally 0 co-occurrences, which would mathematically break everything since the log of 0 is negative infinity, PPMI replaces that with 0 too. It elegantly solves the math problem, leaving us with only the strong positive associations.
Which brings us to our final hurdle in Section 5, fixing rare word bias with a few final tweaks.
See, even with positive PMI, there is one last thing we have to clear up before a computer can reliably map human language. PMI is fundamentally biased toward very infrequent events. Because of how the math divides by the independent probabilities, incredibly rare words get artificially high misleading scores just by bumping into something once. To fix this, researchers introduced two really elegant math tweaks. The first is alpha weighting, where you slightly change the calculation by raising the probability of the context word to a fractional power called alpha. The second is Laplace smoothing. This is where before you compute PMI, you add a tiny constant number, usually between 0.1 and 3, to all of your counts. This effectively shrinks or discounts the non-zero values, grounding those wildly high rare word scores back into reality.
And when it comes to alpha weighting, this specific number is practically magic in the world of natural language processing, 0.75. Back in 2015, researchers Levy, Goldberg, and Dagan found that setting alpha to exactly 0.75 significantly improved the performance of AI word embeddings across a whole bunch of tasks. By raising the count to the power of 0.75, you artificially increase the probability assigned to rare contexts in the denominator. And when that denominator gets bigger, the final PMI score gets smaller, perfectly neutralizing that rare word bias.
And that brings us to the end of our explainer. It leaves us with a pretty profound question to ponder too. We've seen how Fano's theory from 1961, adapted in the late 80s and 90s, uses simple division, logarithms, and smoothing to turn messy text into crystal-clear associations. Knowing how we solve the co-occurrence problem, the negative numbers, and the rare word bias, how do you think these exact same foundational building blocks of probability still drive the cutting-edge, massive artificial intelligence models that we all rely on today? It is literally incredible to think that all this modern AI magic starts with just asking, did these words meet by chance, or are they meant to be together? Keep learning, keep exploring, and thank you so much for joining me for this explainer.